Okay, so good evening, everyone. How are you guys doing? Okay, one answer, doing good. Everybody else, I don't know, but were you guys able to successfully submit assignment 1? It may look easy for some of you who have done, 572, but that's okay. This class is, slow paced, but you really need to understand every line, every variable that you're defining, every command you're calling, and so on. So it's a different, I guess, time scale than some of you who are doing 572, who have already done 572 may feel, but that's fine. Because there are going to be some non-trivial things. For example, last time we were trying to understand bias variance decomposition, right? That's actually, I realized it's part of lecture 5 that, there's a, so lecture 5's notes are also there online. So you can see, I think section 4.2 in lecture 5 is talking about what we did essentially with KNN model, and it also has some notes on linear regression model. Okay. Let me see. So okay, let me ask the question, how was assignment 1? But is everybody able to form groups? I mean, is anybody not in a group of at least 2? Everybody is in a group of 2 at least. Okay, that's good. If there are groups of 2 and they want to combine, they can seek out other groups who are also of size 2 and see if you want to combine, if you want to. Second, I guess, thing which didn't pan out is the classroom change. So that room is definitely better in terms of desk space and so on. But it's fine. We'll see. Classroom scheduling gave us the wrong information. So I'll try to resolve it by next week and see if we have a different classroom. Okay. So how many of you felt that last lecture was too theoretical? Okay, only a few of you. Some of you were fine with. Okay, so sometimes when you see a lot of symbols, you think that maybe it's not practically useful. But as I said, if you look at the learning goals, slides, you'll see that lectures are focused on asking the why question. So that's why we went, into the nitty-gritty depths of what is exactly bias, what is exactly variance. Those definitions. At least variance, you probably know what is the variance of a random variable, but what is bias? It was not clear, and that's what we were trying to do. Algebraically trying to figure out what is bias, what is variance, and where would a model fit in terms of bias and variance. But that's fine. So that lecture was a little bit on the theory side. You will see that. Okay, so this is, I guess, a practical advice that you will see that although we are looking at linear models, linear regression and variations, today we're going to continue looking at linear models. Next class also we're going to look at logistic regression and variants like that. They're all in the linear family of models. You'll see that in the larger scheme of things, you'll probably want to tend towards things like gradient boosted decision trees or random forests. Okay, they are much more complex models. If you think of the bias variance trade-off, they have higher variance. Okay. If you're going to use that, why are we studying linear models? Okay, that's I guess a question that should be at the back of your mind. One practical aspect is that you can start with a complex model and regularize it a lot, and we'll see what is meant by regularization today when we look at a couple of models, LASSO and LASSO and ridge regression. Okay, so you can start with a complex model. Let's say random forest. For random forests, there are ways to kind of control the complexity of the model, okay, by having trees of certain depth or number of leaves and so on. So we'll get to random forests a few lectures from now, but I'm just saying that for complex models, trimming it down to make it less complex is, in practice, seems to be a better thing to do than to start with an extremely simple model like a linear model and make it more complicated, okay. So that's in practice, but but you'll also see that industries like advertising and finance, they prefer interpretable and models where you can kind of make sense of the coefficients, for example. Okay, even in these domains, if you have number of variables like the p we were using is greater than 100 or 1000, then you still have to do regularization. So if you have a 1000-dimensional problem, like 1000 columns in your tabular data, you know, random forest is fine, but even linear models overfit. Okay, so linear models have high variance when the number of variables is pretty high. So you're really trying to kill the variance and go, you know, introduce as much bias as possible, and that's what we will see today. Okay, so that's the I guess rationale behind why we are looking at linear models so far, and we'll kind of jump into nonlinear models soon, but that's the context. Okay. There was a question that came up during the week, which was that there are 2 textbooks, and if you look at my notes, the notes are based on Elements of Statistical Learning book, right? Although the notes are based on Elements of Statistical Learning, if you are new to this whole field of data science, or in general, if the only course you took is probably 572 or not even 572, then you should start with the book, which is Introduction to Statistical Learning with R. Okay, don't worry about the second book. Both books have almost the same content. The book Elements of Statistical Learning is kind of a reference book, so if you're going to be in this career, then it's good to kind of read it. But you don't have to jumpstart and read it immediately. You can start with the Introduction to Statistical Learning book and just focus on that. Don't have to read both books, by the way. And if you can absorb the material, the discussion happening in the chapters of Introduction to Statistical Learning, you'll be in good shape. Okay. And those who are definitely want a challenge can look at Elements of Statistical Learning. Okay. Couple of points about assignment before I get to the learning goal. The assignment solution, first assignment was relatively easy. It was mostly getting used to R, you know, the interface and so on, depending on if you're using RStudio IDE. So solutions may be discussed. I mean, will probably be discussed by the TA in the recitations. Okay, so try to attend them if possible. And the second assignment is out. It has 3 questions, but you know, it's a little bit doesn't tell you the complete story, because each of those questions has a lot of subparts, just like you saw in assignment 1. The first question in the second assignment is related to classification, so you don't have to attack it right now. The second and the third questions are also again from exercises, and they are related to regression. So you can, if you want to get started, start with second and third, and then next week, after covering next week's material, you can jump into 1. Okay, question 1. Okay. So. Okay, so let me quickly go over.
Actually, I have one question.
Yeah.
Like you said, like generally when they do the data collection, they may have huge number of p variables.
Yeah.
Does it make sense to collect that much those much of information?
So the question is, people collect data without, you know, sometimes just because they are concerned if they don't make the measurement now, it will be lost. You know, if you don't make an observation now about some activity, maybe user activity on your website or so on, you will not. If you don't measure it, then you can't really use it for a subsequent decision-making task, whether to change your website or things of that nature, price differently and so on. Because you don't want to have this risk of not measuring something, people measure everything. Okay, and when people measure everything, the database has like too many columns, or your tabular data, your CSV file will have too many columns, and not everything will be relevant. In fact, most of them will be not predictive of something that you care about. That is a challenge, but it's not clear a priori how you decide, because if you know what your downstream task is, then maybe you can hypothesize which variables are important or which measurements are going to be useful to your prediction. But otherwise, it's people are conservative, so they'll measure everything, and then you have a big mess. Even if you're thinking about linear models, you'll have to do something else, and that's the subject of today's lecture. Yeah. Any other question? Okay, let's see. What are the goals today? I think the white background is not a good idea, but So the first goal is to understand what is called subset selection. So subset selection, ridge regression, and LASSO are three types of, I guess, processes or procedures to further bias your linear model. So think of, so far we have been only thinking about, when you're thinking of linear model, we are thinking about what is it, residual sum of squares, and there's one model, there's really nothing to tune, nothing to choose, like KNN at least has a K to pick, right? The linear model did not have anything to choose. There was some closed form expression or something like that, and we really didn't have anything to choose. So here we'll see there will be some choices which will further push the linear model to more biased set of, it'll make it more biased. Okay. So we need to understand why we want to do that, first of all, compared to just doing linear model. I mean, just doing ordinary least squares. Okay, that's the first thing we need to understand. So why do we need more bias? Okay. And the second, and we have kind of alluded to the answer pretty much in the first 5 minutes, but I'll repeat it anyway. The second point is what is the intuition behind ridge regression and LASSO? There are a couple of, I guess, first level intuitions that you can build to understand ridge regression and LASSO, the two techniques, and how they are related to subset selection. Okay, so we'll have the first level of basic intuition, and first point is they are related to subset selection. That's the first point. Second point is they are related to what is called maximum likelihood estimation. So some of you might have seen maximum likelihood estimation elsewhere, but today we'll again revisit what is meant by maximum likelihood estimation. What is likelihood? Okay, why should I maximize it, and so on. So that's the third point. And the fourth point is we're gonna now pick up one item here, ridge regression, and try to really understand ridge regression in terms of principal component analysis. Okay, so that's a little bit more advanced. The fourth point, it needs you to think, get some intuition about linear algebra. So if you're comfortable with linear algebra, eigenvalues and eigenvectors, then that fourth point would be fine to understand what's happening with ridge regression. So these are the 4 goals today. Okay, any questions?
Professor, I have a question with bias and variance.
Yeah.
Is it preferable to have a model with higher bias or a higher variance?
So the question is it preferable to have a model with high bias or high variance, or what is the optimal choice, right? So we want a model which minimizes the EPE. Okay, so let's say we are thinking about regression and we care about squared loss criteria, y minus f of x the whole square. Then we actually we don't really care so much about bias and variance, but we want to minimize the EPE. But which model type? For example, would random forest would be the one which minimizes the EPE, or would something like a linear model would be the one which minimizes the EPE? It's not clear. So that's why we wanted to understand, okay, EPE is composed of 2 or 3 things, something which is irreducible, something we saw last time, something which is like a bias square, and something which is variance. So we understand, okay, complex models may increase one term, but they'll decrease the other term, in the sense of high variance kind of implies low bias for the same EPE, for example. So it's not clear a priori whether we prefer high bias models or high variance models. Okay, is that we care about the model which minimizes our score, whatever the score is, right? Yeah. So let's see. That. Okay, another quick thing I wanted to show is I just gave an example. So this is from Christopher Baer, and there is a URL where they posted this code. Okay, so what is this? I just wanted to show you this code. This is linked on the syllabus page as well, so you can kind of look at how they're performing linear regression. They're actually doing linear regression using gradient descent. Okay, so here is your usual call. So this is actually just one-dimensional linear regression. Okay, so you just have one feature and you have one output. In fact, you can see that x's is randomly picked uniformly, and there's some noise added with some intercept. Okay, and then they're saying, okay, what is the what is the linear relationship between y and x? Okay, and there's some residuals, and they're plotting the yeah, the plotting the okay, is that the plot? I think I should just move this over here. Okay, so they're plotting the data points and the linear fit. Okay, the linear fit is in the blue line, and I mean, so people who are using RStudio can, you know how to. You should be familiar with. You should get familiar with how to use the different panes. There are 4 panes here: the console, the variables, the script part, and then the what is this? I don't know, the last part where you can see the plots, you can see your files, and so on. So this is the usual part. So this is what you would call if you want to just do linear regression. So this is very simple. I mean, you can have other packages called different other functions, even random forest and so on, right? But then from line 19 onwards, they are showing how to think about, think about all these model fitting procedures like linear regression, which is what we have seen so far, in terms of like a gradient descent technique. Okay, so the 19 to 22 is showing what is the loss function. Okay, is this a sum of x times theta? So think of x beta. X is a data matrix, which they okay, I think they do it here, but okay, so x times theta minus y, the whole square, divided by number of observations. This 2 factor is not very critical, but some constant, sum of that. Okay, it's basically sum of squares, residual sum of squares. That's what this objective is. For any theta that I give as input, and given the data x and y's, this is the squared loss. Okay, and then 24 to 26 is saying, okay, I'm going to choose because I'm doing gradient descent. Okay, I'm going to find. So gradient descent is a technique where you're trying to find the gradient of the loss function. This is the loss function. I mean, I'm going to draw it pictorially pretty soon, but this is a loss function. It's some sort of a parabola. Okay, it's because there are squares involved, squares of parameters involved, right? So this parameter 25 and 26 are just saying how many steps of gradient descent I will do. That's 26, and 25 is saying, so gradient descent involves starting with the candidate parameter theta 0, adding some negative gradient to it, getting a theta 1, adding some negative gradient to it, getting theta 2, and so on. So you do it for 1,000 steps. And how much to add? Like I'm adding 2 quantities, with how much of negative gradient to add? It's scaled by a number which is 0.01. Okay, so we'll see the gradient update pretty soon. And here is some bookkeeping. They're just remembering, okay, what were the cost numbers as I increase, as I go from iteration to iteration of my current theta, which is the model. Okay, I'm searching for the best model using gradient descent, right? And the model itself is stored as a list of thetas. And so you start with theta being, I mean, they choose a matrix with zeros. So start with 0, 0 as a theta. So it's a one-dimensional problem, but there's an intercept as well. So my theta is two numbers actually. The intercept, I need to find the intercept. I need to find the coefficient between coefficient which multiplies the x feature. Okay, which is one-dimensional. So here is the gradient descent loop. Okay, so for 1 to n, whatever number of procedures, whatever number of rounds, I need to find the error of my current theta. So I start with some theta, right? So this is the error line. So okay, so error and delta. So the way they've written it is, think of delta as the gradient of the loss with respect to your parameter. So it's actually they're first computing an intermediate quantity which is x theta minus y, okay, and then multiplying it with x transpose. This number is actually the gradient. Okay, it's going to be two-dimensional vector or I guess this type of a matrix, and then you change your theta. So you had a previous value 0, 0. You multiply with 0.01 times this delta. This is the gradient of the loss with respect to theta. Okay, you keep updating this, and these are just bookkeeping, remembering what did I do. I mean, what was the cost at this particular theta, and what was theta value itself. Okay, so 43 and 44 are just remembering what I did, but the gradient update is essentially 40, 41, and 42. Okay, how did they get 40 and 41? Is just the first derivative of the loss function with respect to theta. If you find the do calculus, basically just find the first derivative of the loss, squared loss, which is this, with respect to theta, you will get essentially this delta is that gradient. Okay, it's a vector because theta is 2-dimensional, so gradient is going to be 2-dimensional. And then they're just plotting. So the remaining part is just to show how the gradient updates. I mean, how the thetas change. So this is the. They get disconnected. So on the bottom right, this is showing we started with a theta which is 0 0. So the most horizontal line over here, I don't know if you can actually see the line, but there is a thin red line which is almost flat. Okay, so that's 0 0. Actually no, that's yeah, so okay, so let's not worry about whether that, so that's not theta, so it's theta times, so that's the prediction, so that's my in sample fit line. Okay, and then you can see that line, essentially what this is trying to illustrate is that line is tilting and then going towards the that, you know, figuring out what is the best line fit, and there are thetas corresponding to that. Okay, so the reason why we store different thetas here is to compute these lines as my iterations increase. Okay, and the next plot is showing the cost. So this cost also we are remembering for every theta from 1 to 1000 that we are getting, the cost decreases. It's already around 200 iterations, is already pretty down, so it's flat over there. Okay, so that's gradient descent. So just get a feel for what gradient descent is intuitively. So all that's happening is gradient descent itself needs one parameter, which is how much to multiply the gradient with when I add it or subtract it to the current value of my candidate model, which is theta. That's it, and just repeat it over and over again. Okay, and the rest of it is just to figure out what is the gradient of the loss function with respect to my parameter. Just to give you intuition, most of deep learning is all about doing this gradient descent, and in fact you don't even do gradient descent or figure out the gradient of the loss with respect to parameters by hand. The software to figure out what is the gradient of, you know, you decide a neural network of arbitrary shape and size, and then the software will tell you how to compute the gradients and how to update thetas. Essentially the same procedure is what, you know, you can use it for many different models, maybe not random forest and decision trees, but many of the other things. Actually you can use the notion of gradients for gradient boosted decision trees anyway. We'll get there in a few lectures. Okay, so if you understand this loop for linear regression, this is what you can repeat it for any model. I mean, you can repeat this for ridge regression by just changing the cost. Okay, which I'll talk about what ridge regression is today. You can do it for LASSO as well. You can do it for logistic regression, maybe not just the cost, but also how the data is, you know, for logistic regression there will be a different cost, but essentially the updates will be the same. So the rest of the code will be the same, except the cost will change. Okay, and the data will change because of the classification problem. Yeah.
In practice, is it normally done by gradient descent? I thought there was like this more linear algebra based formula to like very quickly give your code.
Yeah. Yeah, so we saw the linear algebra formula, right? So it was x transpose x, the whole inverse x transpose y. So in practice, this is a I would say this is a better way, just because there's an inverse of a matrix there, which also you can get rid of by solving a system of equations. But in practice, I think this is a general enough template that if you know this, you can pick up any model and say, how do I train it? Just do gradient descent. Okay, most of the models. Okay, but you know that for linear regression, sure, there is a closed form formula, but the moment you add, you know, today we'll see a model called LASSO for which you don't have a closed form formula, although the model is linear, just as, you know, linear regression model. For that you can just use this, although it also has some caveats, but that's fine. I mean, mostly this is a template. Okay.
What is the main objective of this code? That is to find data for which the
Yeah, so we want to find the best model, right? Linear model. So we want to find the model which minimizes the cost. Cost is in terms of my training data. This is my training data. So if you forget about 24 onwards, if I tell you the criteria, find me the best linear model. We saw in one of the previous lectures what is the best linear model, right, for this cost. Okay, it was just there was some closed form expression, right, and we'll probably use it today. But yeah.
So what if the computing the gradient of the function is computationally very expensive?
Okay, so the question is, what if the computing the gradient is computationally expensive? Yeah, there are a bunch of additions and multiplications happening here. For linear regression, it's not computationally expensive. I mean, in the sense of it does depend on the number of observations and the number of and the dimension. Okay, of course, theta is theta is 2-dimensional here, but in general, we have p dimensions, right? So that's fine. So it does depend on the number of observations. If number of observations is 1,000,000, okay, if you have 1,000,000 rows in your tabular data, then yeah, this gradient computation will take a lot of time, because you just have to add up some million numbers, okay, million vectors essentially. So there you can do some tricks, okay. What is called stochastic gradient descent. What it does is it doesn't add up it doesn't compute the gradient over all the data points. If you have 1,000,000 rows in your data, it says, okay, let me just pick some random 50 or 100 of them and find the gradient with respect to that and just move forward in the same loop. Okay, so the only thing that changes is line 40 and 41. So 41 is the one which is the gradient. So if you think that this is the most expensive part of your computation, so by the way, in general, you can profile how much time each line is taking in R, in any programming language. So you should kind of figure out how much time each one is taking by just, for example, printing out the current time, for example. That would be a very simple way, but there are many other ways to find how much is each part of my code, script taking, right? Maybe there's a part of your script which is taking 10 minutes and everything else is taking 30 seconds, then you want to figure out why is it taking 10 minutes, right? So anyway, so you can speed it up, but we'll not get into that detail here. Yeah.
So,
yeah.
as per my understanding of gradient descent, that what you told, it's a computer-based solution to get estimates where there is no closed form solution. Can I think like that?
No, we have a closed form solution here, but we still are doing this.
No, assuming so, there is no closed form solution.
Yeah. When you don't have a closed form solution, by closed form solution, just think of a formula. Model is given by a formula which relates the data to the model. If you don't have that, then this is one computation procedure. Many computation methods to get to the model if you don't have this formula. Yeah.
So in theory, stochastic gradient descent should always give me a little less precise parameter values as compared to the normal gradient, the full gradient descent.
Yeah. So stochastic gradient descent. Yeah. So the question is, stochastic gradient descent is it a little bit worse because compared to the full gradient descent, which is, just think of this as the full gradient descent. This part is the full gradient descent. The answer is yes, because you're using less data per step. You'll be less precise, less precise.
So when I'm sampling my observations, can I do a stratified sampling or stuff like that in order to give it like each and every, you know what stratified sampling is, right? So should I use stratified sample when I'm giving it to stochastic gradient model so that it sees every kind of data, right?
That's a good question. The question is, should I use some clever sampling techniques to subsample my observations if I have 1,000,000 rows, right? So that's dependent on the, given this much information, we cannot really say anything. But maybe in your application, you can think about it. But I haven't seen people do any clever sampling other than just subsample in a very naive way. Just get a few rows of your observation. Okay. Any other question? Okay. So let's start. Okay. Okay, so first I'll start with subset selection, and we'll see later on other things, ridge regression and lasso. But the first question is why? Okay, so what is it first of all, right? So subset selection is essentially if you have p features, right? I want to pick a subset of these features. So I don't want to work with all the 1,000 features that I have. Maybe p is 1,000. I really want to use only 100 of them or 50 of them, which are actually useful for my prediction. As I said, we were talking about making all sorts of measurements, and maybe not all of the measurements are actually related to like click-through rate or something, for example, in advertising, right? So I know that only some of the features. Let's say I know that only some of the features are actually relevant. Then I'll only pick them. That's a priori knowledge. I can just pick them directly. But I don't know which of these 1,000 features are actually useful. In that situation, I need to have a data-driven way to pick some of these features. But my intuition is that only some of these features are useful. I don't know which ones, but I know that only some of these probably are useful. Is the case where subset selection applies. Okay. If you already know which ones are useful, you should of course prune things which are not useful and directly use it. Okay. So what is subset selection doing? If you think of the bias variance as being high here, bias as being high here. So if you think of the bias variance curve, I mean I'm not really drawing the curve. If you think of let's say linear model, the original linear model which uses all the p, there's a beta hat which is p cross 1. Okay, it uses all the features. So that would be, let's say, somewhere over here. Then we're trying to go this way. Okay, and this makes sense when your features are high dimensional and you want to stick with linear family. Okay, but you'll see that if the features are not too high dimensional, you can actually go with more complex models that we'll study later on in the course and control their complexity by regularizing, and so you can do probably better than linear model. Okay, that's not the scenario that we're looking at. Okay, so we want to have so it should be clear that we are introducing bias. Why is that? Very simply, we have p features in that model, and if you're going to move towards the left, if I only use 5 features, let's say somehow I dropped p minus 5 guys, everything is noise or not useful for my prediction, I only pick 5 guys, then this model will be on this side because it will only have 5 parameters. Okay, so 5 numbers versus 1,000 numbers, so this model is smaller. If you just think of the number of numbers used to represent the model, there are only 5 numbers to represent my smaller model, and there are 1,000 numbers to represent the other model, so that's why it's more biased. Okay, so here would be subset, and a couple of other things that we'll see today will also be over there. So how do we do this subset selection? And towards the end of last class, I was trying to describe what cross-validation is, and we'll see an application of cross-validation in subset selection. Okay, subset selection is not the most natural. I would say there is a little bit of choice which is different from the vanilla cross-validation that we saw last time. So we'll see what that slight kink is. Except that subset selection we're going to do using cross-validation. Okay, so for that we need to understand what choices do we have. So we have p features, right? And we can pick 1 feature, we can pick 2 features, we can pick 3 features, all the way to p features. And even in each one, if I say I pick 1 feature, which feature should I pick? There are n choices here, right? Sorry, not n. Oops. Yeah, the p choices here, right? Similarly, for 2 features, there is p choose 2 choices here. Okay, if I want to pick 2 features, this is the notation for combination. So if you have seen the probability refresher, I have introduced what a combination, what a permutation is. So go through the refresher if you have not seen it. If you want to pick 2 features out of p features, this is the number of choices that you can have. Okay, and similarly, here you only have one choice. If you want to include all p features, there's only one way, which is to include all the p features, nothing else. Okay. I mean, if you want an example, if I have 3 features, right, x1, x2, and x3, then this is one choice. x1, x2 is one choice. x2, x3 is one choice. What is x1, x3 is one choice. x1 itself is a choice. x2 is another choice. x3 is another choice. Okay, these are all the choices that I can have. Okay, these are all subsets. Okay, of my 3 features. x3 is a subset. Just picking x3 is a choice, right? Just picking x2 is a choice, and so on. So you see how many choices there are.
2 raised to n minus 2.
2 to the power p minus 1. Okay, you can just this is the number of choices you have. I mean, that number is not very important. I'm just showing an example of how many, these are the choices. For example, if you have 3 features, okay, and you can imagine if you have 1,000 features, there's going to be a lot of choices you need to make. Okay. And sometimes you may have to do group choices. For example, if you had a categorical data, something, a data which says somebody is less than 30 years, greater than 30 years. Is that categorical? Okay, it's binary. So let's say there's a categorical variable like education, whether it's master's, bachelor's, or PhD. Then you may have an indicator variable saying, okay, this person is a master's or not. This person is a has a bachelor's degree or not, or this person has a PhD or not. Okay, there are 3 features now, but you want to kind of consider those 3 features together when you're thinking of subset selection. You may not also, but I'm just saying that when you have categorical variables, you may want to think of together including all the that particular categorical variable or the dummy the dummy variables corresponding to the categorical variable, or you can drop all of them. That's a choice that you may want to think about. Okay, but anyway, so in the vanilla version, these are the choices. So how to find the best subset? Okay, best in terms of the subset which is going to be ideally the one which minimizes EPE, but we don't have that expected square prediction error. Let's say we are doing regression, so we still want to find the best subset. Okay. So in the notes, there are a couple of strategies to find subsets, but I will skip over them because we'll directly think about how to do it using cross-validation routine. Okay, but in the notes, there is a way to greedily pick with no feature first, pick the best feature which minimizes the residual sum of squares, then fix that feature. Out of the remaining p minus 1 guys, pick the next one, fix it, pick the third one. So there is something you can do greedily. Greedily just means fixing one at a time, fixing one feature at a time. But let's not worry about that. It's a tangential detail. Okay. So let's directly talk about how to do it with cross validation. Okay. So remember, so I'm just going to first recall cross validation, which is you break your training data x, right? So I'm representing it as a matrix n times p, break it into few folds. Last time we saw 3 folds, right? Maybe like this, whatever, 3 folds. And we said for each choice we do something. And what is that? For each fold, okay, for each fold, let's say this is fold number 1, fold number 2, fold number 3. Fold just means a chunk of data, okay, of the training data. So I should actually put this tag over here to represent this is the training data matrix, okay. And so for each fold, get a model using remaining, spelling mistake, but get a model using remaining folds, okay. but you don't really care about the model. Get the error. Okay, error or loss for that fold. Okay, let's say fold I, for each fold I. For example, I is equal to 1, 2 and 3 in this example. So for each fold, get an error by getting a model using remaining folds, and get the error for fold I, where you use fold I as your validation or as your test data. Okay, so you built a model using remaining folds, and then you just use that model on the fold that you did not use and get some error metric. Okay, is that clear? And that's it. So once you finish this loop, then you sum these errors or take an average, sum the errors across folds. Okay, sum or average is the same. Sum these errors across folds. So that's going to be your estimate of EPE. This is going to be your estimated expected prediction error. Okay, for that choice. For the given choice, you did this thing, you found this sum over all folds. If there are 3 folds, there will be 3 terms, 3 numbers here, average it. That's going to be your number for that choice. Okay, and you can do this for every choice. Okay, you can do this for every choice. Yeah.
How do the number of folds impact do they or do they not?
Of course they do. Everything that you pick here is going to impact anything, subsequent numbers. It's a computation. Computationally, it's true. So the number of folds and the number of data points that you have an influence, huge influence on this estimate. Okay, but we're not going to look at how exactly they influence this number. Okay, if you have lots of data, you can afford to have lot more folds, and you can have a really good estimate here. Ideally, that would be the ideal situation. But you have less data, lesser folds are better, but they have an influence on this number. Okay, these numbers get influenced by number of folds and the number of data points that you have. So for each choice, and we saw this for k and n. So in k and n, the choices were k is equal to 1, 2, 3, 4, and so on. Right? For each choice, we could have computed these numbers, gotten the estimated EPE for the k and n k choice, and whichever k choice would have led to the smallest number, that's the k you kind of choose to use for any future test point. Okay, is that clear? Any questions about this part? Yeah.
Why is it the sum of errors? Wouldn't it be the average?
I mean, sum and average is the same in the sense of they're proportional, right? Maybe 1 by 3 here, if there are 3 folds, right? You're just comparing equivalent things, so you can compare sums with sums or averages with averages, the same. Yeah, actually, for it to be estimate of EP, it has to be average. Okay. That's correct. Yeah.
So you were saying that is a matrix, data matrix. So
Yeah, there's also Y here, which I did not draw, but you split that as well. Same split.
yeah, and then when you're taking folds, like segregating 3 folds, what is the criteria that you're looking for segregating the 3 folds?
There is no criteria. I just picked 3 as a number. That was my choice. So we are trying to get rid of this kn and k choice, but we did make few other choices, which is the number of folds. So I picked 3 as a number of folds.
But in the folds,
Which data points belong to which folds is your question, right? So I just broke it into 3 directly, like lexicographically. However they are organized, I just broke it into 3 parts. But you will see in several people in the workflow, they actually randomly permute essentially the observations, especially if it's not time series data. There is no relation between one observation, its prediction, and another observation, its prediction. There is no relation. If one appears before the other, or the other appears before the first one, there is no relation. So you can randomly permute them, okay, as in just change the order of your observations and then pick the top 3 in the first fold, next 2/3, next 1/3 in your next fold, and next 1/3 in your next fold. Okay, that's what people do. So there's no, it all comes back to some assumptions being made on the data. I think the most fundamental assumption which a lot of people kind of implicitly make, which is actually not needed for your process, but to understand why this makes sense, the assumption is that each observation is independent of the other, right? So your each x comma y has nothing to do with the next x comma y. So we did this even while thinking about EPE or just thinking about data, that there's a feature and there's a dependent variable. They have a joint distribution between them, p of x comma y. You draw a sample from it, you'll get an x and a y, but your next observation is going to be another sample from the joint distribution, and so these two samples have nothing to do with each other. Okay, they're of course being drawn from the same distribution, but they don't have anything to do with each other. Okay, there is no statistical dependence between these two samples. Okay. In time series, that's not true. Yeah.
Suppose for fold 1,
Yeah.
you are taking folds 2 and 3 to predict the y values of fold 1.
Yes.
And similarly do it for each fold, like for fold 2.
Yes. Yes.
And then you're taking the average of errors across all the folds.
Yes. Yeah.
Which is same as the last class about K and G.
Yeah, this is just for KNN. We're going to get into subset selection, and subset selection will have the same thing. So in subset selection, what do we need to do? For us, the choices are going to be subsets. Okay. But so our choices are going to be subsets, and so for each subset choice, we can compute this, right? There could be too many subsets that we saw, right? There could be 2 to the power p minus 1, where p is the number of variables, right? If p is 10, there is already 1,000 choices. Okay, 2 to the power 10 is about 1,024 or something. So when the number of variables is 10, you have 1,000 choices over which you're going to compute this number and then figure out what is the best one. Okay.
So cutting it row wise or cutting it column wise and trying to estimate the error based on that. So if we have our
This folds. No, you can't cut it based on columns, right?
but on subset selection, if we're only using certain variables.
Yeah. So that's what this was showing. So yeah, we're cutting columns, cutting across columns. Say like we are dropping. For example, if your subset choice is x1 and x3, then you're dropped the second column of your data. Okay, and you're asking whether this subset of variables is actually predicting and is getting an EPE which is lower than other choices. Okay, if this guy's EPE value, right, the estimated EPE in that cross-validation loop is the lowest among all these 7 choices here, the one shown over there, then you will pick that's my best subset. Okay, but there is a variation to this that's also discussed in the notes or in the book. You can do this, what we just discussed. So each subset you get this estimated EPE and pick the best subset. The slight variation to this is you get these numbers, okay, and then you do a slightly different 2-step procedure. First, you figure out which subset size has the lowest number, okay, but there is no number corresponding to a subset size. There is a number corresponding to every subset, right? So what you do is for a subset size, there could be many subsets. You pick the average. You average the errors for a subset size. For example, subset size 1, there will be 3 choices we saw in the previous slide: x1 only, x2 only, x3 only, right? So you'll have 3 numbers, just average them. That's a score for the size of the subset being 1, and there will be a score for the size of subset being 2, and there will be a score for size of subset being 3. Then you compare these 3 numbers. Maybe it will say subset 2 size is the one with the average score the lowest. Then among 2, you know which one is the highest, so which one is the lowest score. Okay, so then among the subsets of size 2, you will pick something, maybe x1 and x3, the one I circled in the previous slide. Okay, a slight change of procedure, but if not, this is fine. This is fine to pick. So as long as you have choices, you can, make the choice in a data-driven way. That's what this is doing. Okay. Any questions? So in the notes, there is a comparison of. They actually show that if you do subset selection, you get a lesser test error than if you just do least squares. Okay, so that's on page 9 in lecture 3, but let's not worry about it. It's a specific data set, so in general it may be either way. Okay. It's good. Okay, so 650. So there's actually so lecture 4 in the notes starts with an application. but I'll pick the application during the break so that it's a good, low, not heavy content. So we'll talk about the application pretty soon. So let's directly go to talk about, subset selection is fine. It lets me make my model more biased. It's still a linear model, but it's a linear model on a smaller number of features. I'm going to now introduce two other biasing techniques and just say that, just show that how they are related to subset selection. Okay. So I keep using one, but the first one is called LASSO, and the second one is called regression. Okay, it's a little bit different than the ordering in the notes, but let's treat them. I mean, we will treat them together anyway. Okay. So what is LASSO? There is a name. There is a full form for that. It's called least absolute shrinkage and selection operator. But let's, it's not very critical what the name means. I mean, there is some meaning for each of those terms, but we'll try to understand intuitively what are these models. Okay. So LASSO is a model which is residual sum of squares of beta, the usual thing. It's all linear models. So residual sum of squares of beta plus some lambda times sum over I is equal to 1 to p of absolute value of beta, I guess j is equal to 1 to p of beta j. Okay. So this is the criteria now. So all it's saying is, okay, I'm going to score my models not just based on how well they do in terms of residual sum of squares, but I'll also score them based on another term, and I'll just add these two numbers. So score based on the first term, score based on the second term, add them together. That's my final score for my model. So what is the model? That's beta. And what is this? This, let's say, so lambda is some number. Okay, so let's think of it as 10 to the power minus 2, which is essentially 0.01. Okay, lambda is some number. Okay, for now let's think of lambda as 0.01. The second term is just saying it's 0.01 times a term which is saying every coordinate of beta, I'm going to look at its absolute magnitude. I mean, each beta j is a coefficient of feature j, right? I mean, beta j times xj, beta something, beta 1 times x1 and so on. So I'm just looking at its magnitude. For a given model, I can tell you what the each coordinate magnitude is, right? It's just remove the sign. If it's a negative number, drop the sign. If it's a positive number, keep it. Add them together. Okay, that will evaluate to some number, positive number, and I add it over all the p features that I have. Okay, so that's my score. So this is my total score for my model now. I just changed it. Previously the score was just the RSS of beta, which was just the sum of squares of y's minus beta transpose xi's, right? So now that scoring has changed. Okay, that's it. That's called a LASSO. It's just fancy, a lot of notation, but this is intuitively at the first step. This is what it is. Okay, just the scoring function has changed. And what does this? Why did we change the scoring function? Okay, we changed the scoring function to mimic subset selection. So both, actually we will see that both ridge regression and LASSO, the first level of understanding is that they are trying to mimic subset selection. Okay, we'll get to ridge soon. What do I mean by that? In subset selection, if I have p features, if I drop p by 2 features, let's say half of them, then I have betas which are, then I'm essentially only computing betas for half of them, right? I mean, others think of the betas as 0. That's the equivalent thing, right? So either I can drop the columns, or I can say that the coefficients of those columns are zeros, right? All I'm trying to say is that beta 1 times x1 plus beta 2 times x2 plus beta 3 times x3 plus beta 4 times x4. All I'm saying is dropping the two features is the same as saying I'll set beta 3 and beta 4 to be equal to zeros each, right? So that's what subset selection is doing. And this term here is saying try to set betas to be 0. So because it's a loss criteria, I want to kind of keep this low. The lowest I can go for the second term is set all the betas to 0, right? That would be the best. If I set all the betas to be 0, which means that my beta model, if the model is all zeros, then that's the best model, right? But I don't want to do that because I know that probably that will not make a good, it will not have a good EPE. Okay, so that's why I'm introducing this lambda. It's balancing between the squared loss, the loss on my training data, and my preference, which is my preference is to set betas to be close to 0. I mean, or 0 itself. Okay, it's trading off the two objectives that I have. Okay. Yeah.
Still have to do cross-validation to figure out which betas to set to 0, or is that like?
So the question is, do we still have to do cross-validation to set which betas to be equal to 0? We are not setting betas equal to 0. So the first point is that subset selection was setting betas equal to 0 equivalently by dropping columns. Here, we just want to find a model which minimizes this total score. Okay. And how do we relate it to cross-validation is that there is still this choice. There's still this choice of lambda. Okay. So maybe you can use cross-validation to figure out what is the best lambda to use. Okay, you can do that. But for a given lambda, you can just think of maybe doing gradient descent, the thing that we saw earlier, and figure out the best beta for this criteria. So previously there was a criteria which was only including the residual sum of squares. You just change that cost function to include that second thing that I wrote. You can easily write that function, second term, and minimize that instead. Yeah.
Why are we actually doing lasso regression? Like, what's the difference between simple linear regression?
Why are we doing lasso? So question is, why are we doing lasso, right? Yes, so that goes back to the previous. So does anybody have an answer for that? Why are we doing lasso and not simple? Not simple linear regression, but just a linear regression without any bells and whistles.
If there are a lot of features, what happens is that the coefficient values are not correct.
Yeah.
That's a problem with keeping too many features.
Yeah.
That's the curse of dimensionality.
Yeah.
So to reduce the number of features, you can do subset selection or do a ratio loss. Yeah.
So we are operating in a space where even linear models are high variance models. So yeah. How do you get variable importance here?
When I look at the summary of the model in a simple linear regression,
Yeah.
I know that some of my features are actually not important, or they are very less important to get the p-values. Right?
So good point. So you're saying, okay, I can just do linear model and look at p-values, and maybe the p-value is high, which means I can. Yeah, so the p-values business depends on a lot of modeling assumptions. That's why I think so there was a small section in my notes, I think from lecture 2, I guess, or lecture 3.
So LASSO also has the assumption that it is assuming that y and x, basically the response and the feature variable are linear in nature.
Yes, all these models are linear, yes.
Exactly, they are making same assumption which linear regression.
No, that's linearity assumption is one assumption. There are 100 other assumptions that also go in, okay.
Yeah, but constructively the backbone is same for linear regression and LASSO.
No, so linear models is the same. Everything else is different. Everything else is where you're saying you should not be swept under the rug. Okay.
But LASSO and Regression fall into the linear family.
Everything falls into linear so far, and in next lecture everything is linear, but there are assumptions involved, and that's where everything breaks down. So if you do ordinary least squares, okay, if you do ordinary least squares, you get a beta hat and you get some p-values, okay. That depends on assumptions that you made about your data, okay. That your errors, residuals are normal, okay. yeah, the distribution is normal. The distribution is normal, and X's features are not random. Under that situation, you can show that recentered betas, which are essentially z-scores, are normally distributed if you know the variance of your residuals. So there's a lot of things assumed to say that, okay, there's this thing called z-scores, and they are actually normally distributed or t-distributed, whichever flavor you like, and therefore I can look at whether that number is large enough. If it is large enough, then my null hypothesis that beta hat is 0 is I can reject the null, right? So there are a lot of things, assumptions being made, which I did not discuss in this lecture. Okay, and we directly went to cross validation because we don't want to make all those assumptions. We just care about performing well in terms of EPE in the future, right? So we have right now one hammer, which is cross validation, to pick the choices, whatever choices we have, so that we can do well in the future. We don't care about p-values, and in fact we cannot even get p-values the moment you do anything else with the data. So for example, if you do subset selection, okay, I got a subset, I got a beta corresponding to a subset. Let's say subset selection, I dropped x2, I got beta 1 and beta 3. There is no p-values for beta 1 and beta 3. The previous procedure that you did for linear regression, that's not the right procedure. There is no way to figure out whether beta 1 and beta 2 are statistic, in some sense. Any statistical significance stuff that you do is not correct for the subset selected version, because you use the data to figure out the subset, and then you're using the data to again compute the betas. Then there is a lot of ways the data is affecting your choice, right? So then you cannot really use the procedures that you talked about, essentially like looking at the summary of the model and looking at the the p-values and deciding whether something is important or not. Whatever you read about linear regression comes under assumptions. You should know the assumptions, right? Nothing is wrong here. Yeah.
About why we are doing LASSO regression, because is it just that because it is helping us to automatically select some features rather than in simple linear regression you have to do all those things manually? Is that the difference? Because
what is the manual way? I mean, this was the manual way. Subset selection is the manual way. What other is the manual way?
Like, say for example, x2 is related to x3. There is no point in choosing x3 because x2 and x3 are highly correlated. So instead of that, just use x1 and x2.
that is variable study.
Yeah. So actually, if you use the LASSO regression, what does is it makes that x3 coefficient as 0. So that's the one way, practical way where you use, like, if there is a high multicollinearity, LASSO regression will reduce those coefficients to 0.
Okay, so I didn't explain that anyway. So that's fine. That's a fine answer. So your question is what? So you are saying, why should I use lasso regression compared to linear regression and then some manual procedures later? Is that your question? Yeah. So they all give me linear models anyway. So which model you choose is best represented by the previous diagram, right? I don't know which model to choose. I don't know which one will give me a low EPE. For example, this is the test error or the generalization error. I don't know which choice to use, even in the linear models. Okay, lasso will give me a sort of different model, beta hat lasso. Linear model will give me a different model, beta hat. That's what I used here. So which model is the best? I don't know. Okay. You have to pick a model, right? So there's no big difference between. You can always use linear model if you think that's the one which is going to give you the lowest square prediction error. That's fine. Okay. The question is, so why use this additional squared absolute value of beta squares, betas? Why am I introducing that term? Why is that needed? So that reasoning is that it's actually mimicking subset selection. Okay. The subset selection is something that you could have done manually. So you could have solved a linear model with all features. Maybe you looked at some coefficients. The p-values are not high. Then you dropped them. That was under some assumptions. Okay, if you know the assumptions, then under that assumptions, it's fine. The procedure is fine. Okay, but subset selection was doing the same thing by just saying that, okay, let me do it a cross validation way. Pick every subset, look at its estimated EP, and whichever is the lowest one, I'll pick that, because that was my criteria. Okay. here we are saying, okay, you don't have to really look at all subsets because there are potentially too many subsets, right? The moment you have 10 features, then there's 2 to the power 10, which is about 1,000 choices you can make. So instead of that, you just minimize this with an appropriate choice of a single parameter, which is lambda, which is I just said 0.01, but you can actually use cross-validation to choose an appropriate lambda. Okay, cross-validation to choose, make that choice, but modulo that, you can just use this. And what the point I want to get to was that this additional penalty term is gonna try to set betas to be close to 0. I essentially said 0, which is what subset selection was doing, which is what dropping variables means. Okay, instead of setting it to 0, it's trying to cumulatively minimize all the values of betas together. Okay, that's this square box here. So it's like controlling which features to include in a different type, different ways to approach the problem. Subset selection is one way, under assumptions, looking at p-values is another way, and this is another way. Okay, but you'll get different models potentially. Yeah.
Is there a process for selecting the lambda, or
because you don't know how to pick lambda, just like KNN, you can pick different values of lambda and try go through the cross-validation loop. Yeah.
So forward selection, stepwise selection, all those methods come under.
Yeah. So there were some greedy techniques for subset selection. They come under subset selection category. Okay. How to how to pick the how to pick the best subset at the end of the day. Yeah. But I did not discuss that. Any other questions? Who's lost at this point? Okay, yeah, question.
I wanted to ask if you are omitting some of these beta because they are correlated. So do you get any other?
I never said they are correlated. We don't know. I mean, this is just, it could be some betas are 0, and it could be that all the features are required. I don't know. It's everything is data driven here, right? Yeah.
Just ask that lambda, does it change with J, or it is the same lambda for all?
It's a single lambda. So in this version, I'm just saying I'll pick so that lambda is just acting as a way to think of 2 scores. I somehow have to balance that, right? So one number could be, the sum of betas could be in some units, and this residual sum of scores, depending on how, whether I'm measuring things in meters or kilometers, it could be some other number, right? So I'm just saying that I'm just balancing those numbers using lambda. Okay, it's a single number, and you can think of varying that over few, it's continuous number, right? I mean, it's something that you can set 100 different values, but maybe I will pick lambda to be 10 to the power minus 2, 10 to the power minus 1, 10 to the power minus 3, just far spaced enough so that I just want to figure out how to balance these two terms, and I'll get a beta, and that whichever beta will have a high estimated EPE in the cross-validation loop, and that's the beta I'm going to use for my predictions. Okay, that's all.
So lambda doesn't have a closed form solution, right? Because this is by trial and error, right? We are picking the lambda.
Nothing here is closed form. So his question was, does lambda have a closed form expression or formula? No, there is no closed form or a formula for the betas or the lambda. Okay. Any questions? Okay. Okay, so what I'm going to do next is introduce ridge regression, and then we'll try to compare these two guys. Okay, and they look very similar, so that's why I want to introduce it. So ridge regression is the criteria. Okay, is going to be residual sum of squares plus, maybe let's call it lambda 1, maybe just to say sum over j is equal to 1 to p of beta j square. Okay. This is it. There's a slight difference between lasso and ridge regression, but this is the criteria. So if you can minimize, think of lambda 1 as another number like 10 to the power minus 3 or something, or 10 to the power minus 2 itself, whatever. And even this criteria is essentially saying I don't want to pick betas. If the first term was not there, what is the best beta? The beta is going to be that beta where everything is 0. Okay. Because then 0 square plus 0 square plus 0 square, all of them sum to 0, right? So of course the first term is balancing, the first term is data driven, which has the features, the actual measurements, and so it's saying, okay, don't set all the betas to be 0, pick the beta which somehow has low enough numbers but also ensures that the residual sum of squares is low. Okay, so that's ridge regression. There's also something called a kernel version of that, but we'll not discuss that in this lecture, called kernel ridge regression. Okay, but ridge regression and LASSO's objectives look very similar. There is sum of absolute values in the left side and sum of squares on the right side. And what I'm going to do is try to do two things. Actually, I want to achieve two things. One is have a pictorial, geometric understanding of why are these two different. Okay, in the sense that this box versus, I guess, a circle. Actually, I should put a circle around the sum, but that circle. So how are they different geometrically? Okay, and the second thing would be how are they different from maximum likelihood point of view. Okay, so that's where I'll bring in some assumptions. Okay, right now there is really no assumptions. I'm just saying this is the criteria. Just minimize this criteria and do something, get the best model. So the first thing is something geometric, pictures. Second thing is what is the likelihood model that kind of corresponds to this criteria. Okay, and so those are two things. Any questions before I jump into those two parts? Okay. So it turns out, and we are not going to really show this, but ridge regression and LASSO, you want to minimize over beta of residual sum of squares of beta such that beta 1 is less than 1 . So I changed, so I wrote the same thing, LASSO and ridge regression, but in a different way. Okay, so you may ask, okay, what are these now strange symbols? At least minimize over beta is minimize over criteria. The criteria is residual sum of squares. That part is fine. But what is the second line that I wrote? Right. The second line is just so ST is just such that, okay, there's nothing there. So this, okay, this is an inequality. Okay, this is this saying search for a good model. I mean the model that minimizes the residual sum of squares, but that model has to satisfy this criteria. So this I guess this constraint. Okay, that's called a constraint. Okay, the thing on the second line on both sides is actually called a constraint. Okay, this form of writing something in two lines. Basically, the first line captures the objective and what you're trying to do, minimize or maximize, and the second line onwards talks about represents constraints. Okay, this is called a mathematical program. For historical reasons, it's just called mathematical program. Okay, it's just a way to represent what are you trying to optimize. Okay, you're trying to optimize for beta. That's your criteria. That's the objective that you want to minimize, and you want to search betas. You're only allowed to search betas such that their one norm is less than 1. Okay, or it need not be 1, but let's say some number. Okay, for simplicity, let's say it's 1. Let's say t. Some number t. So t, let's think of t as like 10 or 100 or something. Doesn't matter. Okay. So it's just saying search for beta, but it's not letting me search for any beta. It's just saying as long as the beta satisfies this one norm constraint, that is one norm is less than t, then I'll plug it into the objective. As long as then I plug it into the objective. If it's the one which minimizes the residual sum of squares, then that's the one I'll pick.
I thought you just told us before that the objective in LASSO is to minimize
Yes.
the sum of squares plus
Yes.
the other.
Yes.
The other.
Yes. This is the objective. lambda times this guy. So this guy in the box is actually the one norm of beta. Okay, is the definition of one norm. So when people write two columns on this side, 2 columns on that side, and subscript 1, it just is the sum of the absolute values of the coordinates. Okay, that's the one norm. Right, this is the sum of the absolute values of the coordinates, right? Here, so that's the one norm, but it's in the objective. Okay, but here I put it as a constraint. Okay, there's a difference, the way I wrote it here and the way I wrote it there, but those two problems are equivalent. Okay, having something in the objective, the second term in the objective with some lambda, and having a constraint in the second line with some number t, they are actually equivalent, and will not go into the details of why they are equivalent. Okay, it requires some knowledge of this mathematical program related basics, which are not very useful for us right now. All I'm trying to say is that, and so at this point we'll just intuit. Okay, when lambda is large, okay, when lambda is large in the previous slide, I want to pick those models for which the betas are as close to 0 as possible, because if lambda is large and the moment I pick a beta which is like a little bit large, there's a multiplier, right? There's a multiplier effect, right? So I better pick betas which are really close to 0 if lambda is large. Okay.
So could this be a way of kind of choosing lambda as well, eventually by setting a constraint for you?
No. So here you still have something, right? T is, so what I'm trying to motivate here is that t is related to the lambda. If lambda is large, t is small. It's like saying, if lambda is large, I prefer, I can only pick those betas which are like, whose coefficients in each coordinate are not really far away from 0. They cannot be far away from 0 if lambda is large. And beta, one norm of beta less than t is just saying that betas, one norm which is the sum of the absolute values of betas, if it's less than t, if lambda is large, I'm saying t is small, which essentially means that I don't have wiggle room to make betas big anyway, right? I'm just saying that these two are equivalent because if lambda is large, t is small, and it's essentially the same interpretation. Okay, and the same thing on the residual sum of squares side. Okay, you had actually let's put a square here because that thing, okay, maybe not this circle, but this thing over here is the norm of beta 2 square. Okay, this is called the norm of a vector. What is the norm of a vector? It's like some measure of some measure of magnitude of that vector. Okay, so this one norm, and that's 2 norm. 1 norm is just the sum of the absolute values of the entries. 2 norm is the sum of the squares of the entries. Okay, some measure of size of the vector or magnitude of the vector. Okay. So this is beta square. So for ridge regression also I did something the same. I mean, I just pushed the second term into as a constraint. Okay. What am I trying to do here? I'm trying to get a geometric idea of how these are related or different from each other. Okay. Both are trying to balance between setting betas close to 0 and the residual sum of squares, right? And I said both are actually related to subset selection. Subset selection was setting betas exactly equal to 0 for some of them and trying out combinatorially, essentially trying out every subset what's going to be the expected estimate of EPE and figuring out the subset. But here we just have to figure out a beta. We have to figure out a lambda, and then for a fixed lambda there's going to be a appropriate model beta, right? Or for a fixed t on the right hand side there's going to be a model beta, right? There's really no too many subsets to consider and stuff. So that's why we want to understand how are these two at least different from each other. And the first point is geometric. Okay. For that, I want to first understand what is residual sum of squares. Residual sum of squares. Okay. How does it look geometrically? Okay. And I'm gonna do that by saying, let me think of a problem where there's only 2 betas, beta 1 and beta 2, which means my x is, my feature, let's say if I consider intercept, then my feature is just 1 dimensional. Or if I don't consider intercept, I have 2 features. Okay. Beta 1 and beta 2. Okay. So if this is my model, which means that my beta is just beta 1 and then beta 2, which means that p is equal to 2, right? then I can, if 2 dimensions, I can actually visualize what this residual sum of squares function is. Okay, this function is gonna be let me draw it this way. Think of this as beta 2 and this is beta 1. Okay, and the third axis is this function, this loss function, RSS of beta. Right? For every beta value on this plane, if I pick a beta model, what is that model? That's a model whose first coordinate is this guy, and the second coordinate is this guy, right? 2 numbers. That's a 2-dimensional model. For that model, I want to figure out what is the residual sum of squares. That's one number. That's on the z-axis. Okay, so some number, let's say over here. Okay, that's the score for that model, right? I'm only thinking about trying to understand what is this objective, the RSS of beta. Okay, turns out that because it's residual sum of squares, this RSS of beta is actually a parabola looking thing. It's essentially a ball. Think of a ball, okay, with a base. So it's going to be something like this. Sorry. Yeah, this is a parabola. Yeah. So what did I draw here? Okay, this is like the surface of the this is like the surface of this ball. So think of this is the shaded region, which is something else. The other side. Okay, this is essentially a ball. Imagine a ball and put the ball on this xy beta 1 beta 2 axis. Then that's essentially the cos surface. Okay, which means that there is some beta at the bottom for which the loss is like the minimal, lowest, and then as you move away from that beta, there's going to be increasing loss. Okay, it need not be so steep. It could be like a flattish ball, but something. It's going to be a ball like this. Okay, and that's why the intuition was that if you just do gradient descent, you can kind of descend on this ball. Okay, kind of easily if you choose that gradient descent had the parameter learning rate or something called alpha that we chose 0.01 in the code. So that will at least that will make you go down. Okay, and the whole business of deep learning is also about something like this cos surface, but it will not be a ball shaped. It will be so wiggly, and lots of valleys and hills, and that's why there's this whole, I guess, a whole course which I teach on deep learning. Okay, so this is a 3D visualization of the residual sum of squares, the objective function. Okay, and what I'm gonna do is actually chop this ball at same values. Okay, I'm gonna chop it at every, let's say on this is z-axis, right? The loss values. So I'm gonna chop it at equidistant locations. Okay. Then the way it's gonna look, if I chop it now, if we are looking at the top view, there's gonna be some beta hat. There's gonna be some circle here, some circle, and so on. It's gonna keep extending. Okay, the ball keeps extending. So this is the top view of this ball. Okay, the ball doesn't look like that, but think of it as so what are these? These are called contour lines. Okay, contour lines are just the lines the points on the function where the function evaluates the same, the points on the input space or in this beta 1 beta 2 space where they evaluate the same loss value. Okay, so there is a beta hat which has the lowest value, the linear regression best model, and there are a bunch of different betas which all have the same loss value. Okay, let's say if I pick this ring, the loss value is the contour value. This is like a thing that you might have seen if you have seen maps, or if you've gone hiking, you might have seen contour maps. Okay, they are the same elevation, or in this case, the same elevation. Okay, so that's the objective. Okay, what I'm gonna do is I'm gonna talk about the constraints. The constraints were 1 norm of beta less than equal to t, and 2 norm of beta less than equal to t. There was a square, but let's not worry about the square because you can always do a square root on both sides and think of that as nu t. Okay, so this constraint on betas in the beta 1 beta 2 space, now we are going to look at beta 1 beta 2 space, right? So that was this was actually beta 1 beta 2 space, the xy plane. Okay, if you look at it, this norm less than equal to t looks like a diamond. Okay, it's not really a diamond, but a shifted, rotated square. Okay, what do I mean by that? There is this magnitude t, so think of this as 0 comma t, it's t comma 0, and the other points are like 0 comma, minus t comma 0, this point, and this point is 0 comma minus t. Okay, that constraint is saying I'm only going to pick a model which is in this region only. Okay, so any point in here, it's going to be such that it's one norm, which is nothing but the sum of beta j values. I mean, in this case, beta 1 and beta 2, the sum, absolute values. Only the points, or only the models inside are the ones which I'm going to consider. Okay, is this clear? And this guy on the side, ridge regression, is the same thing but a circle. Okay, because let me put the square there. So it's beta 1 square plus beta 2 square is less than or equal to some t. This guy is like an equation for a circle. Okay, in 2 dimensions, right? It's x square plus y square is equal to something is a circle, but less than or equal to something is the circle and everything inside. Okay, so I'm only going to consider models which are inside. Is what the second is what ridge regression is saying. Okay, and so these are the constraints. I'm only willing to pick a model from here. Let's say beta hat. What is beta hat? Beta hat is the one which minimizes the which is at the bottom of this ball. Okay, that's this thing here is beta hat. Okay, p times 1 or is 2 times 1, whatever, same thing. That's beta hat. Okay, that's at the bottom of the ball. It may not be inside these regions, right? So I just put beta hat here, same beta hat, let's say it's over here. Okay, it may not be in that region. Okay, the one which minimizes only the first term, but now then that means that I don't want to pick that model because my objective was not to pick, I only want to pick models inside this. Okay, then if you actually draw the I guess contours, or in this case same thing, that's the contours, right? I'm going to look at where does the contour intersect the this feasible region or the region where I'm willing to consider a model. Okay, it turns out that okay, this is not a good diagram maybe. Turns out that if you look at the left side, those contours, they'll most likely hit the corner point before hitting the edge. Okay, in this diagram, the way I've drawn it, it's not hitting the corner point first, but actually let me actually draw the correct way. Like this. Let's say beta is here. So it first hits the corner point before hitting the edges. Okay, that's okay. So it's not. So why is this true? This is true in higher dimensions. In 2 dimensions, it can hit anywhere, edge or the corner point. Okay, that's why I'm just drawing it this way. And the other one was just a circle, and the same thing. There's a beta hat here, and it'll hit somewhere. Okay, somewhere over here, and there's somewhere over here. So this is the model, which is beta lasso, and this is the model which is beta hat ridge. Okay, so models are going to be different. Of course, the models are going to be different from just doing least squares, which was the beta hat. This is the original least squares.
So can you repeat why it won't go inside? Like why they won't be in overlap?
No, it will overlap. I mean, this is a contour, right? So of course it will hit the edges, but in high dimensions it will pretty much. So what happens is, in 2 dimensions there are 4 corners, right? You can see 4 corners on this diamond. So in 3 dimensions it's going to be like really like a diamond. Okay, it's going to have surfaces, and there will be, how many corners it will have? How many corners will it have? 6. Okay, there will be 6 corners, and as you increase the dimensions, is it 6 corners? Yeah, 8 corners. Sorry, 1, 2, 3, 4. Wait, 8 corners? Oh, 8 corners. Okay, now I'm getting confused. Yeah, 4. Yeah, that's true. 4.
There'll be 6, right? And 2 points in each axis, so it will be 6.
Yeah, so there will be 6.
2 points on each axis.
Anyway, I'm just saying that the number of corners increases is just 2 times the number of dimensions. Okay, so it's linear. It's not gonna go in. Yeah.
So when this lasso thing is completed, is it going to tell you the number that you need of I'm trying to find the right word for the subset size, or is it going to tell you the exact beta values?
It'll tell you the exact beta values. So there's no subset selection. So okay, I was just trying to answer this question of why would it hit a corner. I'm just saying that in high dimensions there'll be too many pokey things, too many corners. So the first time your ball hits that diamond shaped thing will be most likely at a corner. Okay, that's just the explanation. Even if it's not at a corner, it's fine. It's going to be such that most of the betas will be close to 0. The corner point is essentially where the beta 1 is 0. If not that we're hitting it, look, we want to pick a model from here. The closest, the one which has the lowest residual sum of squares is this guy. Okay, and this guy has the second coordinate. The first coordinate is 0. Okay, that's all I'm trying to say. If it doesn't hit the corner point, of course the coordinates are both numbers are non-zero. But I'm just saying that there's a good likelihood that it will hit the corner points. Which if it hits the corner points is essentially the same as subset selection because you're dropping the column. Okay, if it doesn't hit the corner points, it's fine. But you'll see that the magnitudes, it is of course balancing the one norm of the model. So of course it will have lower values. Okay, so essentially it's trying to do something like subset selection, but it's not just telling you the subset size. If it hits the corner point, it's literally telling you the beta value for just the second coordinate. The first coordinate is beta value 0. So it's already telling you the model and the subset size. Okay, if it hits the corner point.
And that would be the column to drop?
You already dropped it in the sense if the beta is 0, then you have dropped the column. If one of the coordinates beta is 0, then you have dropped the column.
Beta 1 will be dropped, right? The one on the end.
Yeah, here beta 1 will be dropped. So this is beta 1 and this is beta 2. If this is the corner point, beta 1 is 0. Okay. So in that case, it's not really dropping any points, but it will try to make the magnitudes close to 0 as possible. Like this was the one without the ridge penalty, the second term, and this is the model with the ridge penalty included. This is the best model in this region, which has the lowest residual sum of squares, because as you go away from the contour, what is it?
You're taking the circle as the vertex point as 0, 0.
Yeah, it is origin centered. So these feasible regions are, 0, 0 belongs to this area. I mean, belongs to this constraint region. Okay, but we are not going to take 0, 0. I mean, I'm just saying that we want to pick a model which is in that region but has the lowest residual sum of squares. Okay, here the residual sum of squares is the lowest. Next lowest is here. Next lowest is here. Next lowest is here. So the closer you are to the innermost ring, the lower the residual sum of squares. So you want to pick the innermost ring, the closer ring, but you still want to be in these feasible regions, which are these guys. Okay, that's what's happening geometrically for lasso and ridge regression, and they're trying to approximate subset selection essentially. But of course, it's not exactly subset selection because subset selection is a combinatorial thing. You're looking at every subset and figuring out its estimated EPE and picking out the best subset. Here, we are not doing anything. By picking an appropriate lambda, we have already gotten some model. And the model, if it's lasso type of thing, it will most likely drop some columns. Okay, you're getting it for free. Okay, and that's essentially